The tuning which you implement on your controllers is going to be dictated by the type of process that you would like to go and achieve. A lot of people like to have something such as quarter wave damping. Imagine if my set point was to change, then we're going to find that quarter wave damping with the process variable is going to look something along the following lines. We'll have an overshoot of the process variable, and the next time it overshoots, it'll probably be about a quarter of that value, and then the process variable will settle down to the set point value. This is possibly the most robust and fastest combination of PID that we can go and encounter. But this may not always be what you would like to achieve. A couple of years ago, I was working in a plant where a level was controlled at about 90% of the tank value, and often that tank would start up from scratch. Now, in a case like that, you could not have a situation where you'd have quarter wave damping, because as soon as your process variable got past 100%, the tank would start to overflow. So it would not work under those situations. And that's where you possibly would come in with what we're trying to describe with this video, which is going to be Pessen sum overshoot. So instead of having your process variable go up very high, what we can do is we can have the process variable only go over by a certain amount and then come and the process flow can kick in. So we're not going to get to the 100%, and therefore the tank is not going to overflow. Again, it all boils down to the type of process which you would like to go and achieve. Pessen tuning with sum overshoot has the formulas put up on the board in front of you. It is a closed loop tuning method, which means that you are going to put the controller into automatic, and you are going to take a low gain value, no integral, no derivative, and you will get the process to oscillate exactly the same as the other video that I showed you on the Ziegler-Nichols closed loop tuning. Once you've got continuous oscillations, then the gain value which allowed you to get the continuous oscillations is the Ku that you are going to put into the equation. Pu is the time of one complete oscillation, and again that's going to come from the Ziegler-Nichols closed loop tuning method. I'm now going to do such a demonstration. I've got a controller with a low gain value of 1, and there's no integral and there's no derivative. We put the controller in and we give it a step change, and as you can see, my process is going to be pretty overdamped. So what I will do is just go and increase the gain value, and we'll keep playing around until we can get constant oscillations. The oscillations are now starting, but they do get reduced, so we need to go for a bigger gain, and we keep doing this until we get to our continuous or constant oscillations. As always, you don't want to have any of the pens drawing a flat line at the top or a flat line at the bottom. So you keep increasing your gain until you can get to constant oscillations. So I know that this would be the point at which I would get constant oscillations, and I'm just going to increase it a bit so that you can see what we have got, and that's it. The point at which I get constant oscillations is going to have a gain value of 8.9. So that becomes the Ku value that I can go and use. I also need to know the total time of one complete cycle, and I can either measure from the top to the top or from the bottom to the bottom. If I look at from the bottom to the bottom, it looks like I'm going to have about 1.5 blocks, of which each block is 5 minutes. So it looks like about 7.5 minutes. Now I can go ahead and do the calculation. So all we really need to go and do now is to do our substitution. In this particular instance, my Ku is going to have a value of 8.9, and so you can go and work out the gain. Pu is going to have a value of 7.5, and so you can work out the integral. And Pu again at the bottom is going to have a value of 7.5 divided by 3, and you are going to get the derivative value. take those three values and put them into your controller, and you would end up with Pessen sum overshoot. Now I'm going to open up the controller and put those values in. I calculated a value of 2.67 and 3.75 and 2.5. Again, make it easier for yourself like I do. I've got a spreadsheet where I put all the formulas in and it kicks it out for us automatically. Now we can go and run the process and see exactly what it is going to do. I'm going to drop the set point down and we'll take it from there. So as you can see, there is some overshoot, and it will control the process nicely. It's not quarter wave damping. It's not going to give us as much of an overshoot, but it is going to work effectively for what we are going to require. As you can see, there is going to be some overshoot, and then the process is going to settle down quite nicely. So this is going to be Pessen with some overshoot. Nice and easy and straightforward to go and implement.